What does it mean when a comet seems to breathe these 3A Atlas, a wanderer from a distant star system, exhales 40 kilos of water every second in the icy void far too remote from the sun for such strange behavior? Astronomers murmur, it's acting alive. Yet this comet's tail only grows stranger, nickel without iron cyanide trailing in its wake, and whispers of origins billions of years older than our own star system. Meanwhile, far from this cosmic visitor, citizen scientists uncover the largest odd radio circles ever seen. Mercury and Sirius align with eerie precision in October's skies, sparking questions about a possible connection to 3I Atlas. And Blue Origin's October flight. It raises more mysteries than it solves. Did it even happen? Stick with me to the end as we dive into these unsettling questions in our bold new multi-story format, keeping our late-night listeners in sync with the cosmic pulse above. If these enigmas grip you, like they do me, smash that like button and subscribe to stay in the loop. As this unfolds, live drop a comment with where you're tuning in, from what time it is there, and whether you think we're getting the full story on these world-shaking discoveries. Want to help this community grow? Share this video on X, Facebook, Reddit, or your group chats. You're the reason we keep chasing these cosmic tales. Thank you for having our back. Part 1. The Impossible Signal. Imagine yourself adrift in the frigid void of space far beyond the reach of the sun's warmth, 3 times farther than Earth, where sunlight is a faint murmur. Ice remains locked in an eternal freeze and comets slumber in silence. Then against all odds you see it, a comet blazing with life, spewing 40 kilograms of water into the abyss every single second. Not a drip but a torrent gushing from a frozen rock where water has no right to flow. This is 3I Atlas, an interstellar wanderer from a distant star carrying secrets that defy the rules of our solar system. The first hint of its rebellion came in early 2025 when the Swift Space Telescope, built to chase gamma-ray bursts, turned its ultraviolet gaze toward 3I Atlas. What it saw was unthinkable, a shimmering halo of hydroxyl OH molecules encircling the comet. Hydroxyl is the ghost of water, the fractured remains left behind when sunlight tears H2O apart. Spotting OH means water was just there, and Swift saw it in droves. At 351 astronomical units from the sun, 3I Atlas was unleashing 1.35 827 water molecules per second. That's 40 kilograms every second, the equivalent of hurling a small car's worth of water into space every minute at a distance where our comets barely stir. Our solar system's comets don't behave like this. Out here, they're dormant, frozen relics waiting for the sun's warmth to rouse them. Water ice needs heat to sublimate, to leap from solid to gas without ever melting. But at this distance, solar energy is too feeble to spark such a spectacle. Our comets bide their time, waking only when they draw closer to the sun, trailing gas and dust in their wake. 3I Atlas, though, missed that script entirely. Compare it to Oumuamua, the first interstellar visitor we spotted. That object was a barren, tumbling rock, dry as dust, racing through our solar system without a whisper of activity. Then came 2I Borisov, the second interstellar comet which played by our rules. Active, yes, but predictable, blending in like a local. 3I Atlas is neither. It's a cosmic renegade screaming water into the void where silence should reign. Astronomers are left grappling with a single burning question. What force could drive this impossible flood? Is there an unknown type of ice that sublimates in the deep cold? Could the comet's core still hold warmth from its birth billions of years ago? Does its rotation channel sunlight in some bizarre way, unlocking hidden reservoirs of volatile material? Or is there alien chemistry at work inside this rock? Something we've never imagined. The water is just the start. 3I Atlas is also leaking cyanide, nickel, and carbon dioxide in quantities that defy logic. Each new observation deepens the enigma, every spectral line in the data a fresh question mark. This isn't just a comet acting strange. It's a comet playing by rules forged in another star system under conditions we can't yet fathom. Now every telescope that can track this rogue is locked onto it. Spectroscopy, photometry, polarimetry, every tool in our arsenal. Because 3I Atlas isn't just an oddity, it's a portal. It's a glimpse into a star system we'll never visit, a snapshot of a protostellar disk from billions of years ago. What kind of cosmic crucible forged a comet like this? Is 3I Atlas merely an outlier, or is it a herald whispering truths about a universe far stranger than we ever dared to dream? Through this crack in our understanding, something extraordinary is calling. Part 2. Nickel without iron. Comets, those ancient wanderers of the cosmos, are supposed to obey certain rules. As they bask in the sun's heat, metals on their surfaces begin to sublimate, turning from solid to gas. Iron and nickel, cosmic companions, always appear together, bound like lifelong partners in the mineral structures of every comet we've studied. It's a universal truth, a predictable dance we've come to expect. But 3I Atlas. It tore up the rulebook. In 2025, the Very Large Telescope in Chile turned its spectrograph toward 3I Atlas and revealed something unthinkable. Nickel emission lines burned bright in the spectrum, vivid, unmistakable, impossible to dismiss. Yet iron either absent or so faint it barely flickered. Nickel without iron is like smoke without fire, footprints without a source. In our solar system, this simply doesn't happen. When a comet warms enough to release metals, iron and nickel emerge in lockstep. Their ratio is predictable, their bond forged in the same mineral grains shaped by similar processes, sublimating at nearly identical temperatures. But at 2.8 astronomical units from the Sun, 3I Atlas was hemorrhaging nickel at 5 grams per second, a relentless stream second after second with iron nowhere in sight. This isn't a fluke. It's a revelation, a glimpse into a comet with a composition that defies our understanding. Astronomers are scrambling for answers, each theory more tantalizing than the last. Could chemical fractionation be the culprit? Perhaps in the alien star system where 3I Atlas was born, nickel hitched a ride with volatile compounds that vaporize easily, while iron was trapped in stubborn, heat-resistant minerals. Imagine nickel escaping with fleeting ices, while iron lingered in rocky grains, creating the bizarre decoupling we're witnessing. Another possibility points to organometallic compounds. On Earth, molecules like nickel carbonyl, where nickel binds to carbon monoxide, evaporate at low temperatures. If 3I Atlas formed in a carbon-rich environment, its nickel could be locked in such volatile molecules, breaking free under sunlight, while iron remains bound in solid grains. Then there's space weathering. For billions of years, cosmic rays and ultraviolet radiation have battered 3I Atlas's surface. This relentless assault could have sculpted a nickel-rich outer layer, a radiation-scarred rind that masks the comet's true composition. Perhaps the iron is buried deeper, altered or hidden by eons of cosmic exposure. But the most thrilling idea is this. What if 3I Atlas hails from a star system with wildly different elemental abundances? Stars vary in their chemical makeup, shaped by the unique histories of their birth clouds. Some enriched by ancient supernovae, others forged in distant corners of the galaxy. Could 3I Atlas come from a place where nickel reigns over iron? Its chemistry a direct imprint of an alien star's peculiar recipe. Caution is warranted. Spectroscopy is a finicky art. Faint iron signals could lurk just below detection thresholds, masked by other spectral features, or the wrong choice of wavelengths. As 3I Atlas nears the Sun, heating up further, iron might yet emerge, restoring order to our cosmic assumptions. But what if it doesn't? What if even at perihelion, its closest approach to the Sun, the nickel-to-iron ratio remains defiantly inverted? That would be a seismic shift, a signal that other planetary systems can craft comets with metal chemistry so alien that our models would need to be rewritten from scratch. This is why 3I Atlas has astronomers gripped. Every observation is a crucible, every spectrum a chance to either anchor our understanding or upend it entirely. Right now, this interstellar rebel is shattering more than it confirms, daring us to rethink the very rules of the cosmos. Part 3. A comet that switches on. Comets are supposed to follow a predictable script. As they spiral closer to the Sun, they gradually brighten. The math is simple: more sunlight, more heat, more sublimation, more gas and dust streaming into space. It's a smooth, steady climb, almost routine. But 3I Atlas, it's rewriting the playbook with a flair for the dramatic. Astronomers tracking 3I Atlas notice something peculiar about its hue. Early on, at the distant fringes of our solar system, it appeared neutral. perhaps faintly reddish like most icy bodies lingering far from the sun. But as it drew nearer, something extraordinary happened. The comet began to glow. An eerie, vivid green. Not a subtle tint, but a striking emerald blaze that leapt out in photographs. The source, cyanide molecules, and atomic nickel both radiating powerfully in the green spectrum, their emissions surging as the comet warmed. This wasn't a gentle brightening. It wasn't linear. It was superlinear. The emission lines intensified far faster than the inverse square law would predict. Halve the distance to the sun, and you quadruple the sunlight per square meter. Basic physics. But 3I Atlas's brilliance was climbing even steeper, as if something deep within was being unleashed, some hidden process suddenly igniting. Astronomers call this switch-on behavior a threshold, where a specific ice previously dormant hits the right temperature and begins to sublimate. Gas production spikes, new spectral lines flare, and the comet transforms. It's like flipping a switch, one moment off, the next moment blazing. 3I Atlas seems to have multiple switches. The water came first, gushing at an astonishing 3.5 astronomical units, already an anomaly. Then, as the comet closed and cyanide and nickel kicked in, painting the coma green. Each surge hints at a new reservoir of volatile material, awakening each tide to a distinct chemical threshold. One theory points to extended icy grains in the coma. Picture tiny ice particles lofted from the nucleus by escaping gas, drifting in a frozen cloud around the comet. As these grains float closer to the sun, they warm, each reaching its own sublimation point. Suddenly, the coma itself becomes a distributed source of gas, not just the nucleus, but a halo of icy flecks amplifying the comet's glow and explaining the superlinear brightness. Another possibility is thermal fracturing. Comets are cosmic patchworks of ice and rock. When one region heats and expands while another stays cold, stresses build. Eventually, the comet cracks, exposing fresh, insulated material to sunlight. New surfaces sublimate, new volatiles escape, triggering an outburst. 3I Atlas might be splintering as it warms, peeling back layers of ancient chemistry like pages in a book. Then there are the exotic ices. Water ice sublimates at one temperature, carbon monoxide at a far lower one, carbon dioxide somewhere in between. If 3I Atlas is layered like an onion, each depth or region holding different ices, its warming journey would trigger a sequence of awakenings, first the hyper-volatile ices, then the mid-range ones, and finally the stubborn holdouts. Each layer reveals a new chapter of the comet's story. This behavior isn't entirely alien. Our solar system's comets can be erratic, some flare tenfold overnight, others split under thermal stress, and a few lie dormant until perihelion before erupting into life. But 3I Atlas operates on a schedule that feels otherworldly. It's awake at distances where it should be asleep, switching on with an intensity that feels almost choreographed. As 3I Atlas hurtles toward the sun, the suspense builds. Will more switches flip? Will new molecules emerge, rewriting our chemical maps? Will its activity plateau? Or will it keep accelerating, defying every model we have? Each week delivers fresh data, each observation a twist in an unfolding cosmic drama. This isn't just a comet, it's a spectacle daring us to keep up. Part 4. Where did it come from? Every cosmic traveler carries a story etched in its path through the stars. For 3I Atlas, that story spans billions of years and thousands of light years, written in a trajectory that whispers of its ancient origins. Its orbit is hyperbolic, a celestial arc that doesn't close, a one-way ticket through our solar system. With an eccentricity greater than 1, 3I Atlas is unbound, a galactic drifter sweeping in from interstellar space, grazing the sun and destined to vanish forever into the void. Astronomers traced its journey backward using pre-discovery images, those serendipitous snapshots captured by automated sky surveys before anyone knew 3I Atlas was special. Some images date back to when the comet was 6.4 astronomical units away, still inbound, a cold and distant speck. By weaving these observations together, researchers mapped its trajectory with pinpoint precision, revealing a path that stretches far beyond our solar system, out into the galaxy's depths. With help from the Gaia Space Telescope, which charts the positions and motions of billions of stars, astronomers ventured an astonishing hypothesis about 3I Atlas's birthplace. The galaxy isn't a random scattering of stars, it has structure. most like our Sun, reside in the thin disk, a flat plane of younger metal-rich stars orbiting the galactic core. But there's also the thick disk, a realm of older stars on tilted eccentric orbits puffed up above and below the galactic plane. These ancient stars, born early in the galaxy's history, are chemically distinct with lower metallicity, fewer heavy elements forged in the hearts of long-dead stars. 3I Atlas's trajectory hints it may hail from this thick disk. If so, it could be older than our solar system, which formed 4.6 billion years ago. Thick disk stars can be 7 billion years or more, meaning 3I Atlas might carry ice and rock from a time before our Sun was even a spark. Imagine that a comet forged in a primordial gas cloud. When the galaxy was younger, its chemistry simpler. Back then, supernovae had yet to enrich the cosmos with heavier elements. Early stars were nearly pure hydrogen and helium, while later ones like our Sun boast a few percent heavy elements. Thick disk stars sit in between with modest amounts of metals but abundant volatiles. Carbon, nitrogen, oxygen locked in ices and molecules. This ancient chemistry could explain 3I Atlas's oddities: the high carbon dioxide to water ratio, the strange metal abundances, the nickel-heavy signature. It might be a chemical fossil, a snapshot of a galaxy with a leaner periodic table. Pinpointing its origins, however, is no small feat. Tracing a comet's path through billions of years of galactic chaos, nudged by passing stars tugged by spiral arms, is like following a whisper through a storm. Yet the possibility that 3I Atlas predates our solar system is electrifying. It's a relic, a time capsule from the galaxy's youth. If we could identify its birth cluster, the stellar nursery where it formed alongside sibling stars, and perhaps even planets, we might find traces of its kin, scattered comets, or exiled worlds drifting across the galaxy. 3I Atlas could be a single note in a cosmic symphony, a message written across light years, waiting for us to learn its language. Part 5. What's riding along with it? Comets are more than just ice and rock. They're cosmic couriers hauling the chemical fingerprints of their birthplaces across the galaxy. And 3I Atlas, it's carrying a payload that's as bizarre as it is tantalizing. We've already marveled at the water, 40 kilograms per second, flooding into space at distances where it has no business flowing, its hydroxyl fragments a neon sign of the comet's defiance. But water is just the opening act. The real headliner is carbon dioxide, and its dominance is rewriting everything we thought we knew. In our solar system, comets are water-driven, with carbon dioxide playing a minor role, a quiet backup to the main volatile. 3I Atlas turns that on its head. Observations reveal a staggering 95% of its volatile emissions are carbon dioxide, with water relegated to a supporting role. This isn't just unusual, it's a cosmic inversion. A chemistry that feels alien in our neighborhood. Why so much carbon dioxide? One clue might lie in formation temperature. Carbon dioxide ice condenses at higher temperatures than water ice. If 3I Atlas formed closer to its parent star in a warmer slice of its protostellar disk, it could have stockpiled carbon dioxide while shedding water. Or perhaps its star's radiation field sculpted the ices differently. Or giant planets in that system churn the disk, mixing materials in ways our Sun's planets never did. Then there's the cyanide. Cyanide, Cn, is no stranger to comets. It's the molecule that often paints their comas green. But in 3I Atlas, it emerged late after the water, defying the synchronized sublimation we see in our comets, where cyanide and water wake up together. This delay suggests cyanide might be locked away differently, perhaps trapped in organic molecules that need extra heat to unravel, or buried in deeper icy layers. And let's not forget the nickel glowing green without its usual companion iron. A mystery we've already probed, but one that underscores the comet's strange cargo. Every molecule is a breadcrumb. Every element a clue. Volatiles like water and carbon dioxide hint at the temperatures and pressures of 3I Atlas's birth. Refractory materials reveal how solids condensed and endured thermal processing. The gas-to-dust ratio betrays the comet's structure and fragility. But there's a bigger question looming, one that sparks both wonder and skepticism. Could 3I Atlas carry the seeds of life? The panspermia hypothesis, the idea that life's building blocks hitchhike across space on comets, gets a nod here. 3I Atlas has water, organics, and cyanide, a key player in prebiotic chemistry. It's practically a recipe for sparking life on a barren world. But let's be clear, this is pure speculation. There's no evidence 3I Atlas harbors life, or that any comet ever has. Cosmic radiation is a molecular shredder dismantling complex compounds over millions of years in interstellar space. Ultraviolet light is no kinder breaking down DNA proteins, even simple amino acids. For life to survive, it would need to be buried deep within meters of ice and rock. Yet complex molecules, chemical fossils might endure. Formed in the atmosphere, or on the surface of a distant planet in 3I Atlas's home system, these molecules could have been swept into the comet, shielded enough to survive the journey. If we could study them, they might unveil alien atmospheric chemistry, hint at long-extinct metabolic pathways, or whisper secrets encoded in carbon, nitrogen, and oxygen. This is why scientists dream of chasing an interstellar comet like 3I Atlas, not just observing it from afar, but sending a spacecraft to rendezvous land drill and sample its core. The challenges are daunting. Interstellar objects zip through at tens of kilometers per second, demanding a probe with pinpoint timing or breakneck speed. But the reward: a sample from another star system, a glimpse of chemistry from a distant corner of the galaxy, answers to questions we're only beginning to ask. 3I Atlas is already billions of kilometers away, slipping beyond our grasp. We didn't catch it this time, but it's ignited a hunger for what lies out there, teasing us with the promise of cosmic truths waiting to be uncovered. Part 6. Citizen Scientists Chasing Cosmic Ghosts. Sometimes the greatest breakthroughs come from a single pair of eyes seeing the data in just the right way, not through algorithms or machine learning, but through the raw power of human curiosity and intuition. And often those eyes don't belong to a professional astronomer. Let me introduce you to odd radio circles, or ORCs. If they're new to you, you're in good company. Discovered in 2019, ORCs are practically infants in astronomical terms. These vast circular structures, visible only in radio wavelengths, elude optical and infrared detection. Point a radio telescope at the right patch of sky, and there they are, perfect rings of radio emission, some spanning hundreds of thousands of light years, drifting through space like cosmic smoke rings. Their origins a complete mystery. The leading theory points to galactic winds or shock waves from supermassive black holes, but we're still piecing it together. Orcs are faint, blending into the radio background, making them tough to spot. Automated algorithms trained to hunt point sources or compact objects often overlook these diffuse, sprawling rings. Enter Radio at Home. This citizen science project invites volunteers to pore over radio continuum maps, searching for anything that stands out. They're not hunting for something specific, they're chasing the weird. In March 2025, a volunteer stumbled upon something extraordinary. Rajay 13134, 6.9 so 501320. Not a catchy name, but its story is riveting. This object revealed itself as a pair of intersecting radio rings, twin circles overlapping in a cosmic figure eight. It's the most distant and powerful ORC ever found, discovered not by an algorithm or a professional survey, but by someone who simply volunteered to stare at the stars. The find came from low-frequency continuum maps produced by LOFAR. The Low-Frequency Array, a sprawling radio telescope network across Europe. LOFAR churns out colossal datasets far too vast for astronomers to sift through manually. Automated pipelines process most of it, flagging objects based on brightness, shape, or other criteria. But those pipelines have limits. They're built to catch the expected, not the strange. That's where human pattern recognition shines. Our brains excel at spotting the unusual, seeing order in chaos, flagging something as interesting even when we can't quite say why. The volunteer who found Rajay 13134 6.9 didn't need to understand ORC physics, they just needed to notice something odd and trust their gut. And they were right. But the story doesn't end there. Radio at Home has uncovered multiple anomalies. One volunteer spotted a giant radio galaxy with a peculiar ring structure. Another found a ring at the end of a jet, defying all theoretical predictions. These discoveries would have drowned in the data deluge without human eyes on the case. The lesson here stretches beyond radio astronomy. We're entering an era of overwhelming data. The Vera Rubin Observatory, when it comes online, will generate 15 terabytes of data every night for a decade. No human team can tackle that alone, and no algorithm can catch every oddity. We need both machines to crunch the bulk, and humans to spot the weird edge cases that defy templates. Now let's tie this to 3 Atlas. Could a citizen scientist have caught its anomalies early? Could someone poring over spectral data have noticed the nickel without iron signature before the prose florid? Could a comet watcher have said, hold on, why is this thing active so far from the sun? Maybe, maybe not. But the point is clear: anomalies like 3 Atlas thrive on diverse perspectives. Professional astronomers bring expertise, training, and context, but also expectations and time constraints. Citizen scientists offer fresh eyes, unburdened by what's supposed to happen, free to see what is happening. History backs this up. Amateur astronomer Koichi Itayama discovered multiple comets in a supernova. British amateur Andrew Gray co-discovered a bizarre stellar outburst. These aren't flukes, they're proof of what happens when passionate people with access to data or telescopes look closely at the cosmos. As telescopes flood us with petabytes of data, citizen scientists could become the first to flag the next interstellar comet, the next strange radio structure, the next cosmic puzzle. Professionals will dive in to unravel the physics, but it's a partnership, a collaboration stronger than either could be alone. Part 7: Citizen Science versus Professional Gatekeeping. Collaboration between citizen scientists and professionals isn't always a seamless dance under the stars. There's friction, real gritty tension. Opening the gates to citizen science invites a flood of false positives. Enthusiastic amateurs flagging artifacts or noise conspiracy theorists, seeing alien signals in every glitch. Professional astronomers understandably tread cautiously. Bodies like the Royal Astronomical Society have wrestled with this. Citizen science clears data backlogs, processes vast data sets, and sparks public excitement for discovery. But quality control is non-negotiable. A discovery isn't real until it's verified, cross-checked, and peer-reviewed, a process demanding time and expertise. False positives are a headache. An amateur flags an unusual object, and astronomers might spend days or weeks chasing it, only to find its instrumental noise a satellite trail or a cosmic ray hit. That's time stolen from real breakthroughs. When false positives stack up, skepticism creeps in, and the signal-to-noise ratio in citizen reports plummets. Fatigue follows. Then there's confirmation bias. When people hunt for something specific, they often find it even in random data. Professionals face this too, but training and peer review keep it in check. Amateurs without those guardrails might see patterns like alien megastructures around Tavi's star, or messages in pulsar timing residuals that aren't there. Calibration and error margins add another layer. Professionals know how to gauge measurement uncertainty, distinguishing a statistically significant signal from a meaningless 1 sigma blip. Amateurs might not reporting detections that don't hold up. And then there's bandwidth. If a citizen science project explodes in popularity with countless volunteers flagging anomalies, professionals tasked with follow-up can drown in the deluge. They can't investigate everything, so they prioritize, and real discoveries might get buried in the pile. But these aren't deal breakers. They're challenges. Training can slash false positives. Teach citizen scientists to assess data, quality, recognize artifacts, and estimate uncertainty in the noise drops. Mentorship programs where seasoned amateurs guide newcomers can uphold standards. Tiered validation requiring multiple independent volunteers to flag the same object before it reaches professionals filters out spurious detections. The payoff is immense. Crowdsourcing anomaly hunts lets you scour larger datasets more thoroughly. Multiple independent eyes reduce the chance of missing a real oddity because someone blinked. Diverse perspectives, people from varied backgrounds spot patterns specialists might overlook. Let's circle back to 3 Atlas. Could a citizen scientist have caught its nickel anomaly early? The spectral data is public. Anyone with the right software can dive in. But spectroscopy is no casual hobby. It demands understanding line identifications, wavelength calibrations, and signal-to-noise ratios. With training guidance and a collaborative community, though someone might have flagged the oddity before it hit headlines. The same applies to 3 Atlas's water production rate. Amateur astronomers often contribute comet-like curves tracking brightness over time. Had they been analyzing ultraviolet data from swift train to spot unusual activity, they might have noticed 3 Atlas's superlinear brightening and said this isn't a normal comet before professional surveys confirmed it. Past citizen-led discoveries prove this isn't wishful thinking. The exoplanet transit method detecting planets via tiny dips in a star's brightness has been propelled by citizen scientists analyzing Kepler data. Projects like Planet Hunters have confirmed multiple exoplanets. Amateur asteroid hunters have spotted near-Earth objects missed by professional surveys. Nova hunters observing nightly with small telescopes often beat professionals to stellar outbursts because large telescopes are booked months in advance. The takeaway isn't that amateurs should replace professionals, that's nonsense. We need both. Professionals bring deep expertise, theoretical rigor, and validation. Citizen scientists offer breadth, fresh eyes, and sheer numbers. It's not a rivalry, it's a partnership. In this era of data deluge, that partnership isn't just valuable, it's essential. Part 8. The Coincidence Effect. In October 2025, the night sky delivered a striking spectacle. Mercury, the innermost planet, dazzled in a rare evening apparition gleaming brightly above the horizon after sunset. Ceres, the largest object in the asteroid belt, hit opposition directly opposite the Sun, at its closest and most radiant. Meanwhile, the bizarre interstellar comet 3 Atlas was stealing headlines with its inexplicable activity. On social media, people began weaving connections: Mercury's visibility, Ceres's brilliance, and a comet acting alive. Was this a cosmic alignment? Were the solar system's gravitational field somehow sparking the comet's odd behavior? The answer is a firm no. These events are unrelated, independent phenomena coinciding purely by chance. Mercury's orbit doesn't influence an interstellar comet's outgassing. Ceres's position has no bearing on chemistry unfolding billions of kilometers away. But humans are pattern-seeking machines hardwired to find meaning where none exists. This tendency is rooted in survival. Our ancestors who linked certain berries to sickness or animal tracks to prey outlived those who missed the signs. Our brains are hypersensitive to patterns, sometimes seeing them where they don't exist, a cosmic version of pareidolia, like spotting faces in clouds or hearing voices in static. Throughout history, celestial events have fueled this instinct. Ancient cultures saw omens and planetary alignments, comets signaling divine wrath or the rise and fall of kings. A vivid example comes from 1910 when Halley's Comet returned. Astronomers detected cyanogen, a toxic gas, in its tail, and sensational headlines screamed of a poisonous comet threatening Earth. Panic ensued, people bought gas masks, sealed windows, even took their own lives in fear. In reality, the comet's tail was so diffuse it was practically a vacuum. The cyanogen was negligible, harmless, but the coincidence of the comet's arrival with unrelated events, solar flares, political unrest, earthquakes, ignited mass hysteria. People connected dots that weren't there. We're seeing the same with 3 Atlas. Its genuine anomalies, unexplained activity, odd composition overlap with Mercury and Ceres's visibility, and suddenly narratives emerge. Maybe the comet is awakened by a solar system resonance. Maybe its path is nudged by gravitational tugs. Maybe it's part of a grand cosmic pattern we don't yet grasp. Astronomers have crunched the numbers. Mercury, barely larger than our moon, exerts negligible gravitational pull on an object in the outer solar system. Ceres, even smaller, is less influential still. The combined might of every planet couldn't significantly alter 3 Atlas's behavior at these distances. The comet's antics stem from its internal processes, solar radiation, and unique makeup, not from Mercury's orbit or Ceres's position. Yet facts struggle against compelling stories. Humans crave narratives. Random, disconnected events feel chaotic, unsettling. If 3 Atlas's activity ties to planetary alignments, the universe feels ordered, predictable, meaningful. Without those connections, we're left in a reality where strange things just happen, and that's unnerving. Confirmation bias amplifies this. Once you seek connections, they appear everywhere. Mercury was visible during past comet discoveries. Ceres was near opposition when another odd object was spotted. Never mind that Mercury shines several times a year, or that Ceres hits opposition annually. Never mind that unusual astronomical finds are routine. Our brains cherry-pick the coincidences, ignoring the noise. Social media pours fuel on this fire. In the past, a wild theory about planetary alignments might fizzle out after a skeptical friend's dismissal. Now post it online, and you'll find a chorus of believers. Links, images, and charts of alignment spread like wildfire. Someone adds evidence, another shares it further. Soon, an alternative narrative rivals the scientific one. This isn't about people being foolish, it's about the power of coincidence, and our brains struggle to dismiss it. With thousands of astronomical events unfolding constantly, some will align purely by chance, and those alignments feel profound, even when they're not. This shapes how we interpret anomalies like 3 Atlas. If you're primed for cosmic conspiracies believing alignments matter, the comet's quirks become proof of something bigger. Is it even a natural comet? Could it be artificial, responding to planetary signals, part of some vast cosmic mechanism? These questions lead us to the next chapter, the machinery of hoaxes, conspiracy theories, and how humans transformed scientific mysteries into cultural myths. Part 9, October 2025. Update. Did it even happen? October 8, 2025. Blue Origin's NS-36 mission. 6 souls aboard 11 minutes aloft. 1 enigmatic passenger, their identity cloaked until the capsule kissed the Texas desert. The launch was textbook. The capsule soared, breached the Kármán line, danced in microgravity, then glided back under parachutes to a dusty landing. Success. Another seamless chapter in Blue Origin's space tourism saga. Their 15th mission. Routine almost. That's the story they're selling. ABC News gave it a nod. Medium tossed up an article. A few space journalists fired off tweets. The mystery passenger's name dropped post-landing, a private individual who craved anonymity during the flight, but was fine with fame afterward. Nothing new there. Wealth buys secrecy every day. But here's the twist, the splinter under the skin for anyone obsessed with spaceflight. The silence. A chilling, suffocating void of coverage. No viral clips. No trending hashtags. No TikTok frenzy. No celebrity hot takes, no memes lighting up the feeds. A commercial crew pierced the edge of space, an event that just years ago would have hijacked headlines for days. Yet it barely rippled. 6 humans left Earth, floated weightless, gazed at our planet's fragile curve against the cosmic black, and returned. That's not just news. That's miraculous. It should be. But the internet yawned. Social media scrolled on in hours. The story dissolved like mist. Why, where was the buzz? Blue Origin usually floods the feeds with cabin footage, passengers floating, laughing noses pressed to windows, Earth glowing below. Where were those shots? Why weren't they plastered across every outlet? Why didn't the mystery passengers reveal, spark a shred of curiosity? Who were they? Why the secrecy? These are the questions that should have fueled endless chatter. Instead, nothing. A deafening quiet. It's as if the flight happened in a void not just of space but of human attention. That silence grows louder than any press release. It starts to feel alive, heavy with intent. You can't help but wonder. You start asking the dangerous questions. Did this flight unfold as they claim? Were there really 6 passengers, or was the manifest a mirage? Was the mystery passenger a real person or a convenient story to dodge pre-flight hype? Did the capsule even launch on October 8th? Or was old footage dusted off with a fresh date? These thoughts sound paranoid, like conspiracy threads spiraling into the dark, but when something this monumental should echo and doesn't, the silence itself becomes a question. Compare it to April 2025, just 6 months prior, when Blue Origin's last New Shepard mission detonated across the public's imagination. Not because of a malfunction, but because of who was on board. April 2025's New Shepard mission was a spectacle. Katy Perry, Gayle King, the first all-female crew, high-profile names with millions of followers, a flight engineered to seize the spotlight. And it did, but not the way Blue Origin hoped. Within hours of the live stream fading, social media ignited with conspiracy theories. Armchair detectives dissected every frame of footage, hunting for cracks in the narrative. Hair and zero gravity became a battleground. Did it float naturally? Was it too stiff? Real hair wig or CGI, the capsule's hatch drew scrutiny. Eagle-eyed skeptics posted side-by-side comparisons, arrows pointing to anomalies. Wasn't the latch on the other side last time? Didn't the doors swing outward before? Why does this look off? Then came the wilder claims, green screen studio sets with fake windows piping in pre-recorded Earth views. Passengers' hands looking too smooth, too plastic, like mannequin props. Some even complained the capsule lacked visible scorch marks post-re-entry, as if dust and camera resolution couldn't explain it. Journalists countered with methodical debunking. Hair in microgravity moves erratically, air currents, static random motion, not gravity, dictate its dance. The hatch. Same mechanism across flights. Camera angles and lighting create illusions of difference. Visa reflections distort perspective. Scorch marks vanish depending on landing site and camera quality. But facts didn't douse the fire. For those convinced the flight was staged, every rebuttal was a cover-up fuel for deeper dives. They crafted elaborate theories, building self-sustaining conspiracies that thrived on doubt. Now contrast that with October 2025. 2 flights, same rocket, same profile, 6 months apart. April's mission sparked a wildfire of attention and skepticism. October's a whisper barely audible. One flight drowned in noise. The other sank in silence. And you have to wonder which is more unsettling. The cacophony of distrust or the void where curiosity should be. Part 10. Space Mysteries as Mirrors. The universe keeps hurling curveballs, objects that defy our logic, signals that mock our models, phenomena that unravel our tidy theories. And every time we do 2 things without fail. First, we race to decode the science. Second, we cast our own reflections onto the enigma. Take Oumuamua, 2017, the first confirmed interstellar visitor, a reddish, elongated, tumbling wanderer, zipping through our solar system, accelerating as it left. That acceleration didn't play nice with gravity's rules. Something was nudging it. Scientists scrambled, maybe outgassing invisible volatiles venting like a faint comet. Or perhaps a hydrogen iceberg sublimating silently. Maybe a shattered planet's fragment, its odd shape and spin-catching radiation pressure just right. But then came the bolder leap. Some even scientists dared to wonder, what if Oumuamua was artificial alight, sail a delicate sheet riding starlight's push? That would explain the speed. And if it was crafted, could it be a probe from another civilization, a scout, or maybe a relic drifting junk from a long-dead alien race? Then there's Tabby's star, KIC 8462852, with its bizarre dimming, deep irregular drops in brightness, sometimes 20% or more. No planet could block that much light, and the dips didn't follow a planet's predictable rhythm. Astronomers threw out ideas. Dust clouds, comet swarms, debris from a cosmic collision. But one paper half in jest floated an alien megastructure. A Dyson swarm, millions of orbiting solar panels or habitats soaking up the stars, energy blocking light as they danced. It fit loosely, from odd radio circles to fast radio bursts to the eerie 3-body atlas. Every cosmic puzzle becomes a canvas. We project our deepest questions onto it. Are we alone? Is the universe a cold machine or a purposeful design? Are there others out there? And if so, are they kin or utterly alien? These mysteries don't just challenge our science. They hold a mirror to our hopes, fears, and relentless need to find meaning in the void. Pareidolia is at the heart of it, our relentless tendency to find patterns in the chaos of the cosmos. We see faces etched in wispy clouds, hear phantom voices in the hiss of white noise, and detect hints of intelligence in the strange behaviors of distant stars or wandering objects. This isn't a flaw or foolishness, it's the very wiring of our minds. We are pattern recognition engines built to err on the side of caution. In the wilds of our ancestral past, mistaking a shadow for a predator was a safer bet than dismissing a predator as a shadow. That instinct lingers hardwired, pushing us to find meaning where there might be none. But there's more to it than survival. There's a deeper, almost aching force at play, an existential longing that pulses through our species. We yearn for connection, for proof that we're not the only sparks of consciousness flickering in the vast cold expanse of the universe. Every astronomical anomaly, whether it's a star's erratic dimming, an object's unexplained acceleration, or a comet's peculiar glow becomes a tantalizing possibility. Each is a door slightly ajar that might lead to something extraordinary, something that could rewrite our place in the cosmos. So we push on those doors with fervor, with hope, with an almost desperate curiosity. The three-body atlas with its haunting green coma shimmering against the black void is one such mirror. In its strange ethereal glow, we see our own reflection staring back our insatiable curiosity, our hunger for meaning, our fragile hope that the universe is not just a machine, but a tapestry woven with intent and wonder. This comet with its oddities and mysteries captures our imagination not because it's definitively alien, but because it could be. It's a canvas for our dreams, a beacon for our questions. Are we alone? Is the universe indifferent, or does it hum with purpose? Are there others out there? And if so, are they like us, or so alien that their existence would unravel our understanding of reality? Maybe one day we'll encounter something truly inexplicable, something that forces us to rewrite the laws of physics or confront the reality of extraterrestrial intelligence. Maybe we'll find a signal, a structure, or a phenomenon that defies every model we've built. But that day hasn't come yet. For now, we have the three-body atlas, a comet, yes, but a weird one, a fascinating one. Its green veil and peculiar behavior spark our imaginations. But it's likely just a comet, a natural marvel, carved from ice and dust dancing through space on its lonely journey. And that's enough. Even in its ordinary nature, it's extraordinary. The universe doesn't need to hide alien secrets to be breathtaking. Every natural mystery, every comet, every star, every unexplained blip reminds us how vast, how strange, how utterly wondrous the cosmos is. These mysteries are mirrors not just reflecting our hopes and fears, but illuminating the beauty of a universe that keeps us guessing, keeps us dreaming, keeps us reaching for the stars. Part 11. The Archive of Alien Systems. Picture the galaxy as a vast library, not of books but of objects. Comets, asteroids, rogue planets cast out during the turbulent birth of planetary systems and hurled into the lonely expanse of interstellar space. Each one is a message in a bottle carrying whispers of the star system where it was born. Every so often, one of these cosmic missives drifts into our solar system, washing up on our shores. These are interstellar objects, postcards from alien systems. Not alien in the sense of extraterrestrial minds, but alien in their foreignness, forged in unfamiliar crucibles under distant stars shaped by conditions unlike anything in our cosmic neighborhood. Each object we detect is a singular data point, a fleeting sample from a far-off world's nursery. With enough of these samples, we begin to piece together the staggering diversity of planetary system chemistries across the galaxy. Our solar system's comets born from the same protoplanetary disk share a family resemblance. Their siblings or cousins crafted from the same well-mixed gas, and dust bathed in the same stellar radiation. Sure, they vary some brim with carbon monoxide, others with water, depending on where in the disk they coalesced, and what temperatures they endured. But they're cut from the same cloth, bound by a shared origin. Interstellar comets, though. They're strangers. They hail from distant systems molded in disks with unique compositions, temperatures, and dynamical chaos. Each one we've encountered so far has been a revelation, a glimpse into the unfamiliar. Oumuamua the first was a puzzle dry, oddly elongated, barely outgassing and accelerating in ways that defied easy explanation. It didn't look or act like our comets. If it was a comet at all, it was a breed we'd never seen. Then came 2I Borisov, rich in carbon monoxide, behaving more like a typical comet, but with a gas-to-dust ratio hinting at a colder, stranger formation environment than our own. It felt familiar, yet spoke in a slightly off-kilter dialect. And now, the three-body atlas with its wild, unorthodox behavior, gushing water and carbon dioxide at vast distances, laced with nickel, but no iron cyanide flaring late in its journey. Its chemistry is a language we barely comprehend, a cosmic cipher that challenges everything we know about comets. 3 objects, 3 radically different stories. If these are a fair sample, and it's a big if, then the galaxy's cometary diversity is mind-boggling. Our solar system's comets may be the exception, not the rule. Imagine systems where comets are dominated by nitrogen ice like Pluto's frozen skin, or where exotic compounds we've never dreamed of shape their cores. Each interstellar visitor is a fragment of a larger story, a clue to the myriad ways stars and their worlds are born. This galactic library is vast, and we've only just begun to browse its shelves, marveling at the strange, beautiful tales written in ice and stone. In other star systems, methane might reign as the dominant volatile, shaping comets unlike our water-rich wanderers. In systems with massive stars, the snow line where water ice can condense lies farther out, forcing comets to form in colder realms with exotic volatile cocktails. In systems where giant planets migrate, their gravitational chaos churns the protoplanetary disk, blending materials from disparate temperature zones. The result, comets with bizarre hybrid compositions, chemical patchworks that defy our expectations. Could some carry molecules we've never seen? Compounds that are thermodynamically possible but require formation pathways absent in our solar system. Exotic organics, alien ices, or strange brews that would make a chemist's heart race. The universe is vast and its parameter space is dizzying. Stellar masses, disk compositions, radiation fields, and dynamical environments form an immense playground. Nature explores this playground with relentless creativity, and some of its creations are bound to be weird. Take it a step further. If life hinges on specific chemical building blocks, water, organics, phosphorus, nitrogen, sulfur, then comets lacking these are sterile, incapable of seeding life, or delivering prebiotic chemistry to fledgling planets. Perhaps Oumuamua was just that, a lifeless rock tumbling through the cosmic void carrying no spark of potential. But if even a fraction of comets bear the right chemistry, that fraction matters. Comets are galactic nomads drifting between stars, crossing light years. If they harbor organic molecules, amino acids, or even dormant microbes, shielded deep within their icy cores, they could ferry life's ingredients across the galaxy. This is panspermia, the provocative, unproven idea that life might hitchhike between worlds on comets or asteroids. It's controversial, yes, but not impossible. And the three-body atlas with its gushing water, organics, and cyanide carries the raw materials, not life itself likely, but the chemical seeds that could bloom into life on a hospitable world. Every interstellar object we detect enriches our cosmic library. Right now, we've cataloged 3, Oumuamua, 2I, Borisov, and the three-body atlas, each a stranger with its own peculiar story. In a decade we might have dozens, in 50 years hundreds. With each we'll analyze compositions, trajectories, and activity patterns, building a statistical map of the galaxy's diversity. Maybe we'll find that water-rich comets like ours are common, churned out by most planetary systems. Or perhaps we'll discover our solar system is the odd one, out with water-rich comets a rarity, and most systems spawning dry carbon-heavy bodies. Either way, the answer will be profound. And then there's the dream, the faint, thrilling possibility of finding a comet bearing unmistakable biomarkers. Molecules like phospholipids, complex organics with chirality, or isotope ratios that whisper of metabolism. That would be a revolution, proof that life's chemistry isn't Earth's alone, that biochemistry hums elsewhere in the cosmos. We're not there yet. The three-body atlas, as far as we can tell, isn't carrying life, but it is carrying information, priceless data, encoded in its ice and dust. Every interstellar visitor is a gift, a free sample from a distant system delivered to our doorstep. All we need to do is look closely, study deeply, and let these cosmic postcards tell their stories. Part 12. Nickel, the Cosmic Messenger. Let's dive back into that nickel anomaly. It's not just a quirk, but a cosmic clue. A chemical fingerprint whispering secrets of the universe. Fingerprints reveal where someone's been, and in this case they point to the stars. Stars are the universe's factories, their cores blazing with nuclear fusion, forging hydrogen and helium into heavier elements: carbon, nitrogen, oxygen, silicon, sulfur, iron. When massive stars meet their end in cataclysmic supernova explosions, they birth even heavier elements like nickel, scattering them into the cosmic void. These elements mingle in vast gas clouds, eventually forming new stars and planets. But not every star follows the same recipe. The mix of heavy elements known as metallicity varies. Young stars born from gas, enriched by countless supernovae, boast high metallicity. Older stars formed in the galaxy's youth, when fewer supernovae had erupted, have lower metallicity. Nickel and iron, both forged in supernovae, emerge in slightly different ratios depending on the explosion's nature. Type Ia supernovae, where a white dwarf greedily accretes matter until it detonates, yield a distinct nickel-to-iron ratio compared to core collapse supernovae, where a massive star implodes in a fiery finale. If 3 Atlas are enigmatic comet formed in a system shaped by an unusual blend of supernova types, its nickel-to-iron ratio could be strikingly unique. We suspect 3 Atlas hails from the thick disk and ancient stellar population. Thick disk stars typically have lower metallicity, but their heavy element ratios can vary wildly. If the nickel anomaly in 3 Atlas mirrors the composition of its parent star, this comet becomes a cosmic tracer unveiling secrets of galactic chemical evolution that are otherwise out of reach. Here's why this matters. We can spectroscopically dissect the atmospheres of stars measuring their iron, nickel, and more. But stars are distant and we can only study a tiny fraction in detail. Plus, we can't probe stars that burned out billions of years ago. Comets, however, are time capsules. They preserve the chemical signatures of their birth, offering a window into the ancient universe that no star can provide. If we could cradle a fragment of 3 Atlas, dissecting its isotopes, trace elements, and mineral structures, we'd hold a relic from a star system potentially billions of years old, thousands of light years distant. We'd be reading a saga etched in atoms. Now let's venture into speculative territory, a fringe notion whispered in certain corners. Could metal anomalies like elevated nickel hint at processed materials? Not naturally processed through thermal metamorphism, but technologically processed. Imagine an advanced civilization mining asteroids, refining metals, constructing vast structures in space. Their industry would produce waste slag tailings exhaust with unusual elemental ratios. Industrial processes are selective. Perhaps they extract iron for construction, discarding nickel-rich residue, or use nickel for specialized purposes, dumping the rest. If a comet formed in a debris disk laced with such industrial byproducts, it could carry these anomalous metals. Eons later, that comet ejected, and wandering the galaxy arrives in our solar system. We detect its nickel anomaly and puzzle over it. Let's be crystal clear, there's no evidence that 3 Atlas bears artificial or technological signatures. None. This idea teeters on the edge of science fiction, dismissed by most scientists, yet it's not physically impossible. With no clear natural explanation for the nickel-iron decoupling, even wild ideas get a moment in the spotlight. More likely it's mundane chemistry, nickel bound in organometallic compounds, fractionation during condensation, or some process we haven't yet imagined common in other star systems but rare in ours. What truly ignites the imagination, though, is this: every comet carries a chemical barcode, a unique signature of elements and isotopes. If we catalog the compositions of dozens, even hundreds of interstellar objects, we could map the galaxy itself. By correlating chemical signatures with trajectories, we might find comets from the galactic center differ from those in the outer halo. Thick disk comets like 3 Atlas could reveal age-related signatures, shedding light on ancient stellar populations. Picture a future where interstellar objects are routine discoveries. Our detection technology so advanced we catalog dozens annually. Each undergoes spectroscopic analysis, its trajectory traced backward, its composition added to a growing database. Patterns emerge: comets from one galactic region are carbon-rich, others water-rich. These differences could reflect regions dominated by low-mass stars with distinct planetary disk chemistries, or areas enriched with oxygen by frequent supernovae. 3 Atlas is the first page of this cosmic library, a single data point but a vital one. Its strange decoupled nickel is a reminder that every element ratio holds a story, every anomaly a clue. With patience and precision, we can read these stories, piecing together the galaxy's grand history one comet at a time. Part 13. The Unseen Population. 3 confirmed interstellar visitors in just 7 years. 2I, Borisov, 3I, Atlas, and 1 other. It's a small sample, but enough to crunch numbers and estimate the hidden multitude passing through our solar system undetected. Astronomers have done the math, factoring in detection rates, survey coverage, and the traits of these 3 objects. Their conclusion: at any given moment, a multitude of interstellar objects likely lurk within Jupiter's orbit. tiny, shadowy, and hurtling at blistering speeds, rendering them invisible to most telescopes. We've been fortunate to detect just 3, owing to serendipitous circumstances they passed close to Earth, glowed with just enough brilliance, or crossed a telescope's field of view at precisely the right instant. How many do we miss? Hundreds, thousands, perhaps even more. For every interstellar comet we manage to capture in our sights, countless others likely slip through the cosmic net, too faint to register, too swift to track, or drifting through unobserved patches of the vast celestial expanse. Spotting these elusive wanderers is a formidable challenge, but the horizon is brightening. A new generation of observatories is emerging, equipped with unprecedented sensitivity and the ability to scan vast swaths of the sky with remarkable precision. The Vera Rubin Observatory, currently under construction in the rugged starlit mountains of Chile, promises to revolutionize our view of the cosmos. Every few nights it will meticulously survey the entire visible sky, capturing objects so faint they push the boundaries of detection. From asteroids and comets to fleeting supernovae, anything that moves, flickers, or dares to disturb the stillness of the heavens, this observatory is expected to identify at least one interstellar visitor per month, if not more. Over the course of a decade, this could translate to over 100 confirmed interstellar objects, providing a rich statistical sample to unravel their compositions, trace their distant origins, and estimate their numbers across the galaxy. Adding another layer to this cosmic hunt, the Square Kilometer Array, a sprawling network of radio telescopes rising in the remote landscapes of Australia and South Africa, will offer a unique perspective. By capturing molecular emissions from comets, it can detect those too dim to be seen by optical telescopes, unveiling a hidden population of interstellar travelers. Meanwhile, space-based telescopes operating in ultraviolet and infrared wavelengths will reveal active comets obscured at visible wavelengths, further expanding our reach. Each of these cutting-edge instruments sharpens our ability to spot these swift, ghostly voyagers as they streak through our solar system. Yet detection is merely the opening act. The true challenge lies in studying these interstellar objects in detail. Moving at tens of kilometers per second relative to the Sun, these cosmic nomads offer only a fleeting window for observation, turning scientific scrutiny into a high-stakes race against time. Despite the difficulties, every new tool brings us closer to unlocking the secrets of this hidden population. Each interstellar object we study serves as a precious fragment of the galaxy's grand, untold narrative, offering clues to the formation, evolution, and diversity of distant star systems. With each passing year, we stand on the cusp of a new era of discovery, poised to capture the stories of these celestial wanderers and weave them into our understanding of the universe. Part 14. Chasing Cosmic Wanderers. By the time we spot interstellar objects, analyze their orbits, and plan follow-up observations, they're often already slipping away. One-Eye Oumuamua was outbound when we found it, a fleeting glimpse before it faded into the cosmic dark, too faint to pursue. Two-Eye Borisov was a rare wind caught inbound, giving us months to study it. Telescopes worldwide tracked it, capturing spectralite curves and detailed data, the ideal scenario. Three-Eye Atlas spotted early is yielding valuable insights, but soon it will hit perihelion, whip around the Sun, and vanish into the void unless we act fast. Ambitious proposals for interstellar object intercept missions are taking shape. Imagine spacecraft on standby, ready to launch at a moment's notice, equipped with powerful propulsion to match the blistering speeds of these visitors, tens of kilometers per second. These probes would need instruments to analyze composition, structure, and perhaps even collect samples. The challenges are daunting: rapid response launches, high-velocity rendezvous, and precision engineering, but the rewards monumental. Picture landing on an interstellar comet, drilling into its ancient surface and collecting ice and rock from a distant star system. Returning those samples to Earth would unlock a scientific treasure trove. Precise isotopic ratios could reveal nuclear processes in the comet's parent star. Complex organic molecules unstudied by remote observation might hold clues to prebiotic chemistry, perhaps even amino acids, or if we're extraordinarily lucky, fossilized microbes. Even without signs of life, every molecule, mineral, and isotope would illuminate the chemistry of alien planetary systems in exquisite detail. Mission concepts are already on the drawing board. Budgets are being pitched. This isn't science fiction, it's engineering, tough but feasible. In 50 or 100 years, we could catalog hundreds of interstellar objects, intercept a dozen, and return samples from several. That data would transform our understanding of galactic comet populations, planetary system diversity, and even the prevalence of life's building blocks across the cosmos. 3I Atlas is a tantalizing preview proof that interstellar comets aren't rare oddities, they're abundant, tumbling through the dark, carrying secrets of the galaxy. The unseen population awaits us, each object a piece of the puzzle. One by one we'll find them, study them, and unravel the mysteries of how planetary systems form, how chemistry varies across the galaxy, and perhaps, just perhaps, how common life truly is. When anomalies collide time, there's 0.5s. Let's pull back and see the full picture, because 3I Atlas isn't the only strange thing shaking up astronomy right now. Not even close. Odd radio circles, enigmatic rings of radio emission with no known origin. Fast radio bursts, fleeting millisecond-long pulses of radio energy blasting from distant galaxies, their cause still a mystery. Tabby's star, with its bizarre, inexplicable dimming patterns. Oumuamua, the interstellar wanderer with unnatural acceleration. 3I Atlas, a comet defying logic with impossible water output and metallic oddities. And these are just the headliners. Dozens, maybe hundreds of lesser-known anomalies lurk in the shadows. Transient events that dodge known categories. Spectral signatures that shouldn't exist, objects moving in ways that defy simple answers. Astronomy is grappling with a flood of phenomena that don't add up. This is new. For most of the 20th century, astronomy was parked for data. You aimed a telescope, snapped a photo, or a spectrum, and pored over it for months. Discoveries were rare. Anomalies even rarer. When something odd appeared, it stole the spotlight because little else competed for attention. Now we're swimming in data. Automated surveys churn out terabytes nightly. Sky catalogs track billions of objects. Gravitational wave detectors capture cosmic collisions. Radio telescopes sweep the heavens non-stop. We're spotting more than we can possibly chase down. A torrent of data unleashes a cascade of cosmic enigmas. When you scan a billion celestial objects, even a 1 in a million anomaly translates to 1,000 tantalizing mysteries. Most of these oddities are brushed off as mere instrument malfunctions, fleeting data glitches, or simple misclassifications. But a select few are undeniably real, and sifting through them to uncover their secrets demands meticulous effort and time. We find ourselves in an era where the sheer volume of anomalies surges far beyond the reach of our current theories, leaving us both awestruck and overwhelmed. We're detecting phenomena at a pace that outstrips our ability to explain them, creating a thrilling yet precarious moment in scientific discovery. It's thrilling because these unexplained mysteries are the sparks that ignite groundbreaking advancements in physics. Consider the pulsars, those cosmic lighthouses pulsing with uncanny precision, or the explosive gamma-ray bursts that baffled astronomers until they revealed secrets of stellar cataclysms. Even gravitational waves, once mere theoretical whispers, emerge from perplexing observations to reshape our understanding of the universe. Yet anomalies are a double-edged sword capable of inspiring awe or sowing doubt. Every peculiar signal or unexpected dimming is swiftly heralded as the next great cosmic revelation, perhaps evidence of alien megastructures. Elusive warp drive signals, enigmatic wormholes, or tantalizing clues to the nature of dark matter. The media amplifies these possibilities with breathless headlines, and the public hungry for cosmic wonders laps it up. But more often than not, 9 times out of 10, in fact, these mysteries unravel into something far more mundane. A veil of cosmic dust, a flicker of instrument noise, or an object misidentified in the vastness of space. The risk lies in what follows. When potential aliens repeatedly dissolve into just dust, public trust in science erodes. Some dismiss these overhyped claims as reckless speculation, while others dig in convinced that scientists are either mistaken or concealing some grand truth. Tabby's star stands as the quintessential case. When astronomers proposed the alien megastructure hypothesis to explain its bizarre dimming patterns, the idea set social media ablaze and sent news outlets into a frenzy. The notion of a distant civilization constructing vast structures around a star captured imaginations worldwide. But as follow-up observations rolled in, the evidence pointed to a more prosaic culprit, wavelength-dependent dimming caused by clouds of dust, not solid alien-built structures. The backlash was swift and unforgiving. Some accepted the dust explanation as a triumph of rigorous science. Others rejected it, accusing researchers of error, or even orchestrating a cover-up to hide evidence of extraterrestrial intelligence. Yet Tabby's star remains an enigma worth studying. The dust model, while compelling, doesn't fully account for the star's complex long-term variability, which dances in ways that defy simple explanation. It might be the remnants of a catastrophic planetary collision, a swirling debris disk, or something entirely beyond our current grasp. This is the essence of science: methodical, iterative, and profoundly valuable, even if it's not the alien blockbuster the public yearned for. The pursuit of truth, not headlines, keeps the cosmos endlessly fascinating. The takeaway: anomalies are opportunities. They force us to rethink models, explore new mechanisms, and question assumptions. Even if they don't rewrite physics, they push it forward. Oumuamua's anomalous acceleration, likely from outgassing, made Comet scientists dig deeper into low-temperature sublimation, exotic ices, and surface properties. That's progress. 3i Atlas is another chance to learn. Its impossible water production challenges our grasp of volatile activation at vast distances. Its nickel anomaly forces us to rethink metal chemistry and comets, something we've overlooked because our comets rarely show strong metal emissions. Its carbon dioxide dominance raises questions about protoplanetary disk conditions in alien systems. When anomalies stack, patterns emerge. Could odd radio circles and fast radio bursts share a common thread, like energetic outflows from galactic cores? Might interstellar objects like Oumuamua and 3i Atlas hint at distinct populations with unique formation paths? Anomalies don't just tease breakthroughs, they demand we keep looking. Could the flood of transient astronomical phenomena reveal something profound about the universe's raw energy? Or are they just unrelated oddities surfacing now because our tech finally catches them? Either way, the answer teaches us something. The trick is balancing skepticism with wonder. You can marvel at an anomaly without proclaiming it rewrites physics. You can explore wild ideas without clinging to them. And when new evidence rolls in, you can pivot without hesitation. This is where science communication shines or stumbles. Take 3i Atlas. Responsible scientists and journalists should say this comet's acting strangely. We're exploring several possible explanations. Here's what we know so far. Not alien comet, defies physics or scientists baffled by impossible object. But nuance doesn't chase clicks. Restrained language rarely goes viral. So the hype machine churns, inflating every anomaly into a potential revolution, only to deflate when a mundane explanation lands. The fix isn't to hush up anomalies. It's to embrace honesty about uncertainty, lay out multiple hypotheses, and update as evidence evolves. Treat the public like adults who can handle ambiguity because they can. Most get that science is a process, that answers shift, that we don't know yet is a valid stance. 3i Atlas is one piece in a growing stack of mysteries. It's compelling, but it's not proof of anything yet. It's a data point, a puzzle, a chance to learn. Whether it's just an odd natural comet or something entirely new, the process of studying it, testing ideas, ruling out possibilities is what matters. That process is science. And science, when done with integrity, is one of humanity's greatest triumphs, especially when it wrestles with the unknown. Part 15. Final reflections, alive, yet utterly natural. Here we stand, thousands of words deep in the enigma of 3 Atlas, an interstellar comet spilling water into the void where water shouldn't exist. It glows with an eerie green, laced with nickel and cyanide, flickering on and off as if guided by intent. This cosmic wanderer carries the chemistry of another star system, perhaps a relic from a distant epoch of the galaxy's past. Is it alive in a poetic sense, perhaps? Its dynamic, ever-shifting, reacting to its surroundings. It springs to life when it should lie dormant, its behavior hinting at purpose, though we know it's governed by the cold logic of physics and chemistry, not will. But alive in the literal sense, almost certainly not. No trace of biology exists here. No metabolism. No reproduction, no intricate dance of information storage and transfer. None of the signatures of life as we know it. 3. Atlas is a frozen rock cloaked in ice warmed by starlight releasing gas and dust in obedience to physical laws. Yet those laws conjure something extraordinary, something we've never witnessed. Water sublimating at astonishing distances, nickel without iron, carbon dioxide reigning supreme, a peculiar on-off rhythm hinting at a complex internal structure or exotic ice compositions. Each observation deepens the mystery, layering the puzzle with new questions. So what is 3 Atlas? The most plausible answer is a natural comet forged in conditions alien to our solar system. Perhaps it formed far from its parent star in a frigid realm, where carbon dioxide ice outshone water ice. Perhaps its star's unique composition birthed strange metal ratios. Or maybe billions of years adrift in interstellar space weathered its surface, reshaping its chemistry. The organometallic hypothesis tantalizes nickel-bound and volatile compounds like nickel carbonyl could explain the peculiar emissions. It demands specific chemical conditions at formation, but nothing impossible, just rare. The thick disk origin theory captivates. If 3 Atlas is 7 billion years old, bearing isotopic echoes of an earlier galactic era, its oddities begin to make sense. Ancient ice, ancient chemistry, ancient minerals, all preserved in the deep freeze of interstellar space, now unveiled as the comet warms under our sun's gaze. Could 3 Atlas be artificial, a probe? A derelict spacecraft, a technological artifact? The evidence says no. Nothing about 3 Atlas demands a technological explanation. Every quirk, every anomaly can be traced at least potentially to natural processes. Invoking extraterrestrial origins is unnecessary, a leap too far. But let's indulge the idea for a moment. If you were to craft something to endure an interstellar voyage detectable billions of years later, how would you do it? You might encase your payload in a comet-like shell, shielding it with ice and rock. You'd weave in chemical signatures, oddities that scream for attention in a spectral scan. You'd let natural sublimation unveil those markers as the object nears a star. Pure speculation, of course. No evidence supports this. Yet it's worth noting an artificial interstellar object might masquerade as a comet, a peculiar one, but natural enough to fool us at first glance. Is 3 Atlas that? Almost certainly not, but the fact that we're even asking speaks volumes. This comet is strange enough to spark wonder, to stretch our minds, to nudge us toward possibilities we'd usually dismiss. And that's its true value, not whether it's natural or artificial, not whether its chemistry is merely odd or groundbreaking, but that it forces us to think. It challenges our assumptions, reminding us that the universe is vast and wilder than our tiny corner of it. Nature has had billions of years and trillions of star systems to play with chemistry. We've only begun to glimpse what's possible. Every interstellar visitor is a test. Oumuamua shook our understanding of cometary activity. Two-eyed Borisov upended our assumptions about carbon monoxide. 3 Atlas defies everything: volatile budgets, metal chemistry, activity distances, compositional diversity. The path forward is clear track. 3 Atlas, as it nears perihelion, measure everything. Spectral light curves, gas production, dust to gas ratios. Hunt for new emission lines. See if iron emerges or if the nickel anomaly holds. Compare data to models, refine them. Make predictions, test them. Embrace for the next interstellar wanderer, because more will come. The galaxy teems with these drifters, and our detection tools sharpen yearly. Each one brings a new puzzle, new clues, a fresh window into how planetary systems form across diverse stellar realms. One day, we might intercept one. We'll land on it, drill into its core, retrieve samples. We'll probe its isotopes in Earth's labs, study its minerals under electron microscopes, scour its organics for prebiotic molecules. We'll uncover truths we can't yet fathom. Until then, we watch, we measure, we wonder. Because that's what we do. We gaze at the cosmos and ask questions. Why does 3 Atlas blaze with activity so far from the sun? Where did it come from? What can it teach us? These questions alone hold immense value even without answers, because questions ignite exploration. 3 Atlas journeyed from somewhere out there across light years and billions of years, bearing a message etched in water, nickel, and cyanide. We didn't ask for this message and we don't yet know its meaning, but we're listening. We're watching. We're learning. In that act of learning and our relentless drive to understand, we find something that feels almost alive, not the comet, but us. Curious, wondering, reaching out to grasp something from impossibly far away, striving to read a letter from another world. The universe keeps sending these letters, cosmic postcards, messages in bottles, visitors from the dark. Each arrival reminds us we inhabit a vast, ancient, unfathomably rich cosmos, one that will always outpace our grasp, always surprise us, always offer new mysteries. 3. Atlas is one such mystery, one comet in an infinite sky, but it's our mystery now. Whether it's merely a chunk of ancient ice or something more, whether its secrets unravel swiftly or resist for decades, we'll keep looking, we'll keep asking, we'll keep listening for what the universe whispers. That's what it means to be human, to spot something strange in the night sky, and refuse to look away, to demand answers even when the universe stays silent, to find wonder in a spray of water, molecules 40 kilograms per second glowing, with improbable nickel tracing a path back to stars we'll never reach. We are small. The universe is vast. Yet between us and that vastness, between our telescopes and these distant comets, between our questions and the answers we chase, a conversation unfolds. It's a slow dialogue spanning centuries and light years, written in photons, spectral lines, and orbital mechanics. 3. Atlas has spoken. We've heard it, and we're still listening for what it might reveal next.